Okay, we're working on section 6.6 in Algebra 2. The name of the section is Properties of Logarithms. And we're going to start out a little different and work on some expansion and condensing. We have three properties that we deal with in logarithms. The first one is called the product property. The product property basically says that if we have the log of a product, base b, that we simply can add the two together, whatever those values are. And I want to point out that this is what we call the condensed version of the law, and this is what we call the expanded version of the law. Okay, and we can go from the condensed to the expanded, or we can go from the expanded to the condensed, whatever way we need to do to solve a problem. For example, if we had the logarithm of 5 times 4, or 20, and notice that it has no base, because the lazy American concept, when it has no base, we assume that the base is 10. So this is a common logarithm. That this is equal to the log of 5 plus the log of 4. And we could actually, on your calculator, we could actually find this because your calculator does give common logarithms. But this is called the condensed version and the expanded version. Now I'm going to show you ways that we use these to actually help us to figure out values. I'm going to look at another one here. The log of x plus the log of y. Now and this would be base, this is base 5 on both. Now we have what we call the expanded version, or expanding, and we want to put it into condensed. So we can do the log of x, y, the product of x, y, base 5. And so what this clearly shows us is that we have the product property being used to expand and condense. I want to look at a couple more examples, at least one example, where we can actually, what I said here, we can have the log of 9 base 2, and we can expand that into the log of 3 times 3 base 2, and we could write it as the log of 3 base 2 plus the log of 3 base 2. So there's several different things that we can do with the product property. Okay? Going along that same lines, if we have a product property, we also have a quotient property. Okay? And the quotient property says that if we have the log of m divided by n base b, that we have the log of m base b subtract the log of n base b. So with the product property we had addition. With the quotient property we have subtraction. Okay, notice it's got to be the same base, but we can, this is the expanded form and this is the condensed form. So an example of this might be example for the log of 7, or excuse me, the log of x over y base 7 equals the log of x base 7 minus the log of y base 7. Okay. Now I'm going to shorten this down because you've seen that the product property had 3 examples. The quotient property works kind of the same way, only using subtraction. And the last one we're going to talk about is the power property of logarithms, which says this, that the log of m to the power of p base b equals p times the log of m base b. So what happens to the power is it comes out front and is multiplied by the logarithm. Okay? So if I can, we've kind of used all 3 of these. This one is pretty straightforward. If I could show you an example that might use several of the properties at once. For example, if we had the log of x to the 7th over y to the 4th base 3. Okay, here we have division and power rules working together. Okay, so if I say, if I start to expand this, I would say the log of x to the 7th base 3 minus the log of y to the 4th base b, and then I apply the power rule. So what I've done there is apply the quotient rule. Now I apply the power rule. So I have 7 log of x base 3 minus 4 times the log of y base b. And there I have it in expanded form. Okay? Let's take a look at this example where I have the log of the 4th root of a, b, c. So the product of a, b, and c. All right, and it's the 4th root. If you think about this from earlier algebra, we learned that the 4th root is the log of a to the 1/4 root times b to the 1/4 root times c to the 1/4 root. And that is all, and remember that our base is base 10. It is a common logarithm. So now we have the product rule and the power rule working together. I'm going to separate it into the 3 by adding them together using the product property. And I'm just going to add them, that's addition, and I take the logarithm of c to the 1/4 power. And remember, it's all to the common log. Now I can apply the power rule. Now the 1/4 comes out in front, and you can write it as 1/4 of log of a, or you can write it as the log of a over 4, because 1/4 times the log of a is log of a over 4. You can also do the same with this. That is a fancy plus sign there. Let's make that a little, okay? The log of b over 4 plus the log of c over 4. And this is the expanded version of the log of the 4th root of a, b, and c. Okay, now what I've done here, both of these, I have taken the condensed version and put them in expanded form. What I want to look at now is taking the expanded form and putting it into the condensed. All right, so I would take maybe a problem that had 15 times the log of f base 6 plus 5 times the log of b, as in vampire, base 6. This is a expanded form version of the logarithm. So I'm going to apply the rules of condensing it. The first thing I'm going to do is, with this one we kind of, we did the product property first and then the power. It's kind of a reversal now. We go back and put the power, we do the power rule first when we're going from expanded to condensed. So this is the log of f to the 15th power base 6 plus the log of v to the 5th power base 6. We apply that product rule in reverse, and now since we're adding them, this is the log of f to the 15th times v to the 5th, and notice we don't have to use a raised dot because they are variables, and so we reversed the process and wrote it into a condensed version. Okay? And kind of on the same lines of this one, maybe we have the log of 7 over 5, and here we have a common log of 7 base 10 over 5. So we are dividing, plus we have, if we look at this, this is the same as the 1/5 times the log of 7. So the same thing applies down here when I said that when you brought the 1/4 out, you could have 1/4 log of a, you can have 1/5 log of 7, which is, if I do the power rule, the log of 7 to the 1/5 power, which we can write in radical form as the log of the 5th root of 7. Okay, so just to kind of reiterate here, we have the product property, the quotient property, and the power property. We can apply all three to whatever version we want to do, going from an expanded to a condensed, or a condensed to an expanded form, okay? One thing it does allow us to do is it allows us to maybe solve a logarithmic equation, okay? For example, if I had solve the log of x base 6 plus the log of x minus 9 base 6, and that equals, let's say, 2, okay? This is what we call a logarithmic equation because it involves logarithms. We apply the process of, this is an expanded form, we apply the process of condensing it. Since it's addition, these are to be multiplied, so what we have is the log of x times the quantity x minus 9 base 6 equals 2. Now, if you look at this, we can write both of these. We can take this particular one and change it from logarithmic form to exponential form. So when you have this situation, what you have is 6 to the second power equals this quantity. That's what this means in exponential form. So what we have is x times x minus 9 equals 6 to the second power. We can take the log out because we wrote it in exponential form. So what we then have, if I use the distributive property, is this, and I put it all on one side. Minus 36 equals 0, and I factor. This can be factored as x minus 12 times x plus 3. So there are two possible answers, 12 and a negative 3. Okay? Now, you can double check these values on your own. I don't have room to do it here, but if you put 12 back in here, you'll find that it is a true, makes a true statement. However, if you put a negative 3 back in, there isn't 6 to any power that equals a negative number. Therefore, this negative value is an extraneous root, and my value is 12. My answer is 12. So we can use the concept of condensing and expanding to solve a logarithmic equation. Okay? On that same lines, sometimes we are given a value of one or the other or a combo, and we are asked to find other values. Let me give you an example of that. Okay? For example, let's say that we had these directions. It said use the log of 5 base 2 is approximately, that means approximately, 2.3219, and the log of 3 base 2 is approximately 1.5850 to find, okay, the following, all right? And I don't remember what example I was on. I think I'm on number 10. For example, we could find an estimated value of something like the log of 25 base 2. We have been given two values with the base 2. It's very important that whatever you look for, that it's in base 2. If it's not going to be able to find using this method, okay? So what we do is we use the concept of the properties that I talked about. We rewrite this 25 either as a factor of 3, 5, or 2. Now I'm going to explain to you a little bit about 2, but I can either use 5, 3, or 2 to break this up. I know that 5 squared is 25, so I can rewrite that as the log of 5 squared base 2. Using the power rule, I can put the 2 in front, this 2 in front, so I have 2 times the log of 5 base 2. So what that tells me is I do know the log of 5 base 2 to approximation, so I can substitute that value in, and I can take 2 times that, which is 4.6438. Now you understand something. I did not use an approximation, but this is an approximation to 4 digits of the log of 25 base 2. Okay, let's take another one. This one's a little bit lengthier, and it's a little bit harder. I have to come up with an idea of what, using the values of 5, 3, and 2 to get 0.6. I do know that this is the log of 3 times 0.2 base 2. And if you multiply that out, 3 times 0.2 is equal to 0.6. So using the product rule, I can say, well, this is the log of 3 base 2 plus the log of 0.2 base 2. Okay? Now it gets a little weird. I do know the log of 3 base 2, and I can substitute that in at any time. I choose not to do it at this time, but I can put this in at any time for that. Okay? But I still have to work with this. 0.2 happens to be the fraction 2 over 10, which is, if I simplify it down, 1/5. So this is the log of 1/5 base 2. I hope you all understand that. I'll go through that again. 0.2 is 2/10, and if I simplify it, is 1/5. All right, now I'm going to keep this log of 3 base 2, even though it is equal to this approximately. And I'm getting the log of 1/5. I have to rewrite this as a power of 5, because I do know 5. And if I do that, that is the log of 5 to the minus 1 power base 2. How do I know that? Any number with a negative exponent is 1 over that. All right? Once again, I'm going to keep this as log of 3 base 2 plus, and I'm going to apply the power rule. So I'm going to bring the minus 1 in front, so I have the log of 5 base 2. Now I have the log of 5 base 2 with the negative 1 as its coefficient, or out in front of it. So now I can plug in 1.5850 for that, and I can take a negative 1 times 2.3219. So I would take that, that becomes negative, that is positive. When I add those two together, I get a negative 0.7369. Okay, so I have used the powers of logarithms, plus I've used condensing. Now I keep saying that you can use 2 also, and even though they didn't give us the log of 2 base 2, you have to understand that the log of 2 base 2 equals 2 to what power equals 2? 2 to the first power. So I can use that concept. Let me give you an example. The log of 10 base 2. All right? I can write the log of 10 as the log of 5 times 2 base 2, which is the log of 5 plus base 2, sorry, the log of 2 base 2. So I do know that the log of 5 approximately equals 2.3219, plus 2 to the first power is 2, so that is plus 1. So my value is 3.3219. Remember that all 3 of these are approximations. And we're just using the concept that was given. So anytime you're giving logarithms what the value of, you can use those to solve for other values by making combinations that add or that multiply or have a product of these values. Okay? So we've talked about the properties of logarithms. We've expanded and condensed to expansion. We've looked at how to solve it using those concepts, and now we look at actually finding values of logarithms given different values for logs. All right.